Hello everyone! In those uncertain times, one thing is certain, you gotta keep coding. Only those who feel they deserve success will get it. So, puff up your chest. Feel entitled to do some coding, to do some algorithmical problem solving. That's what we're here for. Enough said. Let's go now to LeetCode.com. Open weekly contest 219 and go through the problems which were given last Saturday. Now I didn't solve them all. As you can see here, I solved only 3 out of 4, but I'll make the effort to explain them to you one by one, including the one I didn't solve. First problem, 1688, count of matches in tournament. You're given an integer n, the number of teams in a tournament that has strange rules. If the current number of teams is even, each team gets paired with another team. A total of n divided by 2 matches are played, and half of the teams advance to the next round. If the current number of teams is odd, one team randomly advances in the tournament, and the rest get paired. A total of n-1 divided by 2 matches are played, and n-1 divided by 2 plus 1, the one random teams advance to the next round. Return the number of matches played in the tournament until a winner is decided. There is a simple solution to this problem, which immediately comes to mind, and that solution is simulate the games. Start with n teams and see, as you're progressing to the end of the championship, how many matches are played on every round. First round, you will have n divided by 2 matches plus 1 extra if the number is odd. And so you do exactly that. You add to the result n divided by 2. And then if there is an extra team that cannot be paired with anyone, you do n modulo division by 2 and add that to your total. Then you reduce the number of teams by half and you do the same next round, and so on until there is only a single team left. Very simple solution. However, there is an even simpler one, and it looks almost like magic. The correct answer actually can be solved in constant time and is always n-1 for a given n. Why is that? If you think about it this way, every game has a loser. Whenever 2 teams play, one loses. And so every team, except for the winning team, participates in a single game in which they are losers. There is a 1-to-1 mapping between these n-1 teams which lost the game and the number of games played. Right? Think about it. Half of the teams will lose on the first round, then a quarter of the teams will lose on the second round, and so on, until n-1 teams have lost. If at the end the team that won the championship could play with themselves, we would count them as well in that total, but obviously once they're left to a single team, we're done, the championship is over, and so we don't count that team. And therefore, the answer is n-1. Tricky. Simple, yet brilliant. I didn't come up with it during the competition. Would have felt good if I had. Alrighty. Problem 2. Partition into minimum number of decibinary numbers. A decimal number is called decibinary if each of its digits is either 0 or 1 without any leading zeros. For example, 101 and 1100 are decibinary, while 112 and 3001 are not. Given a string n that represents a positive decimal integer, return the minimum number of positive decibinary numbers needed so that they sum up to n. What they're telling you is, we'll give you a number, break it down into numbers that only contain ones and zeros. There's a little shiny aha moment in this problem. The way you would get every digit would be to add ones to get to it. So if you have at any position a digit, let's say 7, you would have to add 7 ones to get to that digit. And then if you have smaller digits, you can always add zeros as a filler. The answer here is find the maximum digit in your number. If this is my number, the maximum digit is 9. And then you would need to add at the very least 9 ones here, right? There is no shorter way to do it. We keep doing this until we get to 9. And then for the other positions, you can do as many ones as needed, and then add zeros as padding for the remaining numbers that we are summing up. And so this is what exactly the solution is. Find the biggest digit within the number and return it. That's the number of elements you need to sum to get the result. Simple solution once you realize that you can look at all the digits independently. And that was problem number 2. Embarrassingly simple if you click, and you better click fast because the next problems are more challenging, especially problem number 4, but wait for it. Before that, let's take a look at Stone Game 7. And as you guess, there have been Stone Games 1, 2, 3, 4, 5, 6 before that. It's very popular on LeetCode to play Stone Games. Alice and Bob take turns playing a game with Alice starting first. There are n stones arranged in a row. On each player's turn, they can remove either the leftmost stone or the rightmost stone from the row and receive points equal to the sum of the remaining stones in that row. The winner is the one with the higher score when there are no stones left to remove. Bob found that he will always lose this game. Poor Bob, he always loses. So he decided to minimize the score's difference. Alice's goal is to maximize the difference in the score. Given an array of integer stones, where stones I represents the value of the ith stone from the left, return the difference in Alice and Bob's score if they both play optimally. They say Bob is trying to minimize the difference, but really what's happening is they follow the same rules. Try to maximize their score, which will minimize the difference between the two scores. So they didn't need to explain that Bob is trying anything fancier or that he will be losing the game. Like, why would they call Bob a loser? Like, how does that help anyone? Anyway, very standard dynamic programming problem. What I implemented was a top-down dynamic programming, meaning I would use memoization. Call the same method again and again, and whenever we call it with the previously used parameters, we would return the result from the cache instead of calculating it again. You can also implement bottom-up solution, and it's with better running speed here. Also, you could eliminate the whole idea of having Alice and Bob and treating them differently because, as I said a while ago, you could treat the problem as if every player on their turn is trying to maximize the sum of the remaining numbers. That's the optimal strategy. What did I do? First, I calculated the sum of all stones. Instead of this approach, I could have used prefix sum array and calculated sums on the fly, but you see how I used the total stone sum and on every move updated it. This helped me provide the sum computation in a constant time in every call to my method move. Get the initial sum of all the numbers, initialize the cache with -1s, and the state has 3 variables. The index of the left element, the index of the right element, and the player whose turn is it now. What's the recurring relationship here? We have reached certain left and right ends of the array. We have a current player, and that player needs to decide their next move. If left and right indices have already met, if we're at a single remaining element, then we might as well return 0 because you have to remove that element and you always have a 0 sum left from the remaining 0 elements. If the result is in the cache, return it. Otherwise, if it's Alice's turn, player equals to 0, then calculate what's better, to remove the left or to remove the right element. And removing the left gives you the sum of the remaining elements minus that left element, plus whatever is the result from the next move of the opposing player, which is Bob. The same is the calculation if you remove the right element. The sum of all remaining elements minus that right element, plus whatever is the result of Bob making their next move. And you make sure that you take the maximum of those two moves, left or right. Else, if it's Bob's turn, Bob is looking to minimize the score, and so we're subtracting his moves from the total. We can either remove again the left or the right element. Make sure to remove from the difference from our final score the remaining sum minus that element that Bob has removed, plus whatever is the result of Alice's next move. And of course, Alice will try to maximize her next move, the same way Bob is trying to minimize his current move. So this is a standard min-max kind of a problem where one of the players is trying to minimize the score and the other is trying to maximize it. Again, because Bob is trying to reduce the score, we're taking the minimum of his possible left and his possible right move. We cache the result and then return it. And so we progress deeper and deeper through that recursion until we reach those single elements, and from there, on our way back, the best moves for the two players surface until at the end we return the total score, the difference between the two players, with Alice making the first move. DP problem, one of its most canonical representations here. Alright. And without further ado, let's drop all those problems behind us, because they were relatively straightforward. And let's move to the problem that had so many ahas that at the end I was like, Maximum height by stacking cuboids. Given n cuboids where the dimensions of the ith cuboid is cuboid I equals to width I, length I, height I, choose a subset of those cubes, fine they're not cubes, cuboids, and place them on each other. You can place cuboid I on cuboid j if width I is less than or equal to width j, length I is less than or equal to length j, and height I is less than or equal to height j. You can rearrange any cuboid's dimension by rotating it to put it on another cuboid. Return the maximum height of the stacked cuboids. There are several considerations here. First, what comes natural to people, if like you don't read carefully the problem, which I guess occurred in my case as well, is you can think that only the length and the width of the object on top needs to be smaller than the one on the bottom, right? It's logical that the height shouldn't matter. However, it matters. They're telling you explicitly here that the height is also smaller or equal of the one below it. And this condition, all of the three dimensions being smaller once you put an object on top of another, is very important because it allows you to create an order. It's possible for A and B cuboids not to be comparable, but if they are, then one would be smaller than the other. And so your solution will be of that type, where you can have, of course, alternatives here. B1 and C1 or something like so. You will have cases in which you will have cuboids that are incomparable in between them, but still they will be comparable to other cuboids. For every cuboid you will have some that you can put below it that are bigger than it, and some that are smaller and you can put on top. Okay, this is the first thing. Now the second important idea, which is not super intuitive, is you should always put the longest dimension of every cuboid as their height. And that won't break the order of the cuboids. Why is that? It's important to realize you can rotate the cuboids any way you want. And therefore you might as well sort their dimensions. Here is what I've done. For every cuboid, we can assume that the shortest is, let's say, length. The middle one is width. And the longest dimension is height. The middle and the short dimension don't really matter whether they'll be width or length or how would you swap them there. It's important though the longest dimension to be height, because this way you maximize the height of the stacked cuboids. And also there is a guarantee that if you use height as the longest dimension, you're not damaging the order of your cuboids. You still can use the same cuboids that are stuck in order, no matter which dimension you choose as height. So you might as well choose the longest one, which maximizes your result. There is a mathematical proof why you can always take the height. But intuitively, if I can explain to you so, rotating the height to become the longest dimension, if you do that for every cuboid in that series of cuboids that can be stacked together, you will be certain to preserve the relationship. And this is because of this requirement that width is less than width and length is less than length and height is less than height. So in other words, if you sort them and you assume the shortest dimension is length, the middle dimension is width, and the longest dimension is height, you should be fine. I didn't come up with this thought. I wish I had. It didn't come to my mind. Also, I didn't initially correctly read this requirement. I thought the requirements of what can be put on top of what are limited to width and length, and the problem is different in this way. Okay, and so once you know that, now it's a matter of first, as I said, sorting the dimensions within the cuboid, the single cuboid, and then sorting all cuboids, put the biggest guy at the bottom, put the next on top, and so on. However, because there can be multiple ways to stack them, this problem now becomes very similar to longest increasing subsequence problem. Once you've sorted your cuboids from the biggest one to the smallest, you will go in order, and for every cuboid, you will see what's the maximum stack that can be built with that cuboid at the top. The trivial cases, we have only that cuboid. And so at the very minimum, we'll have DP is our dynamic programming memorization cache. We'll have the height of the cuboid itself. You will check for every cuboid before it, that's bigger than it potentially. Is it in fact bigger by every dimension? And if it is, if the current cuboid can be placed on that cuboid, then you will record a new maximum if putting the current cuboid on top of the stack ending on this previous cuboid is better than what's our current maximum for I, for our current cuboid. So you will do that for every cuboid that's potentially bigger than ours, as long as they're satisfying this condition. And that's why I'm saying this is very similar to longest increasing subsequence. Just the check here is different. We're checking not only if the element is bigger than the previous one, like in the case of natural numbers, integers. We're checking here whether all the dimensions of the current element are smaller than those of the previous one, which would satisfy the condition and would make it a subsequence. And at the end of it, we find the maximum height from all possible heights from stacks ending on every possible cuboid. This is this calculation here, and we return it. And that was it. A tricky problem, no doubt. I wish it had come to me, but it didn't. I wish I was smarter, but I wasn't. I wish, and I'll keep wishing. This was all for today. I hope you found some of those problems instructive and interesting to solve. And with my 3 problems solved, I got 937th place. Hey, I got some badge as well. I solved them, as I said, in 30 something minutes. The first 3. For the 4th one, I spent another good hour just scratching my head. Very thoughtful expression on my face and no results. Let's see who gave those problems. First problem was not asked by any company. Second problem was asked by Nutanix. Third problem was asked by Dunzo. Hey, we know Dunzo. They had a problem a couple of competitions ago as well. And the hardest one, the stacking cuboids, was asked by Samson. That was it. See ya next time.